Welcome back, everyone. Now we're going to take a look at what I like to call terrestrial evidence of Earth's rotation. Now, in the last video, we learned about evidences of Earth's rotation that we see when we look into the night sky or the daytime sky. But we're looking away from the Earth. We're looking into the sky to observe this evidence. So the question now is there evidence of Earth's rotation down here on Earth? We'd call that terrestrial evidence, because terrestrial means having to do with the Earth. And the answer is yes, there are two terrestrial evidences of Earth's rotation that we need to be aware of. The first is known as the Foucault pendulum. Now, notice the pronunciation. I know if you haven't taken French, you might be tempted to say that that's Foucault, but no, that's a French name. It's Foucault, the way it's pronounced. Now, it says in 1851, French scientist Léon Foucault started a large pendulum swinging for many hours. Over time, the pendulum appeared to be swinging in a different direction. Okay, so now let me show you what this looks like. So this is what a pendulum is: any large, free, swinging mass. Whether it's a mass on the end of a string or a mass on the end of a stick, if it's free to swing from some sort of point, that would be what's called a pendulum. Now, I'm going to show you a pendulum at a museum in Chicago, which is going to be a classic example of the kind of pendulum Foucault started in motion. So let's take a look at this Foucault pendulum at a museum in Chicago. I'm going to fast forward quite a bit.
Now, it may not seem very peaceful because there's a lot of noise in the background, but you want to have a quiet moment.
Well, I'm going to actually add our own narration here. So here's this large pendulum swinging back and forth. And notice we have these sort of bowling pins sort of standing up here. And you'll notice that the pendulum is swinging back and forth, and it appears to have knocked all these pins down. And on the other side, it appears to have knocked all these pins down. So now the question is, when is it going to knock down this pin right here? Well, let's kind of cheat a little bit and fast forward. So, well, that, let's try to go a little further. And a little further still. Oh, we're getting very close to this particular pin right here. Notice that? And I'll fast forward half hour or so. And you can see how close it's getting to this pin now. And finally, oh my God, is that close? Look at that. It almost brushed right against it. So, let's see how many swings it's going to take before this pin finally gets knocked over. So back and forth, the Foucault pendulum swings until eventually bear with us. I'll return the live sound of the video so you can share in the excitement that the audience here must have felt.
I wonder if it'll go over all at once. I know, it's like it's so
close.
Suspenseful. I think the next swing, I think it moved it a little. See, it's nudging it. Oh! Whoa! Oh! Not yet, but soon. Oh! Got it!
Okay, so what's actually happening here? Well, what's actually happening here is the pendulum's not really changing direction. It's the Earth beneath the pendulum that's actually moving. The Earth beneath the pendulum is rotating, and that's causing the target in front of the pendulum to be in motion. So a new target moves in front of the pendulum. And Foucault discovered this in 1851. So what actually happened was that the Earth had been rotating beneath the Foucault pendulum. Okay, so that's your first evidence that the Earth is actually rotating, or terrestrial evidence here on Earth that the Earth is rotating. Now, there's another even more important evidence here that we notice, which actually owes its history to military warfare. Something like 500 years ago, they discovered that cannonballs fired very, very far away would appear to be missing their target and hitting to the right. Now, this particular phenomenon was identified and described by a scientist named Coriolis. It's called the Coriolis effect. Now, what it states is that any object fired over a long enough distance will be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. That would be the Coriolis effect. Now, they noticed this at first with cannonballs and so on. So the Coriolis effect also influences missiles fired on Earth today. Wind actually is affected by the Coriolis effect. The direction the wind goes changes because of it. And even ocean currents, because they are pushed by wind. So there are, anything that's kind of flying along without a pilot is going to be deflected or tilted or redirected by the Coriolis effect. That's because the Earth is rotating. Now I'm going to show you a couple of quick little videos of the Coriolis effect in a smaller environment. Here we have children on a playground, and excuse the poor quality of the video. But notice they're on this merry-go-round sort of apparatus that goes round and round, and when they try to push the ball straight across to their partner, if this huge disc that they're on is spinning, the ball is going to be deflected. Now watch. Look at that. The ball does not go straight in the direction that you intended it to go. It actually appears to be deflected. So you're trying to send, the child in yellow is trying to send the ball to the child in green. But instead, what happens is the ball winds up going to the child in blue. Okay? So the spinning of this disc, this merry-go-round, is what made that happen. And that is called the Coriolis effect. And the Coriolis effect is going to come into play in quite a few chapters in Earth science. It's actually very important. It's going to come into play when we talk about weather and climate. So now, let's talk about how this works. And let's try a couple of problems. The Coriolis effect deflects free-moving projectiles, or wind or whatever, to the right in the northern hemisphere and to the left in the southern hemisphere. Now, so let's take a look at how this is going to work. First, let me show you something that's not in your packet. Okay, here I have a street intersection right here, and I tried to make a car, but it wasn't going to work, so we have now a round car. All right, who knows? Maybe they'll invent a round car one day. You never know. So now here's an intersection. Now we're driving along, and if we make this turn right here, like that, did that car make a left or did that car make a right? What kind of turn did that car make? I'll do it again. The car is coming this way, and the car makes what kind of turn? Did the car make a left turn or a right turn? Well, I hope you're all saying that the car made a right turn, because that's what it did. We're looking ahead, moving forward, and we turned to our right. Now I'm going to make it a little trickier. This car is coming down the road like this, and the car makes this turn like this. Did that car make a right turn, or did that car make a left turn? I will do it again. Here comes the car. Driving along, makes the turn. Did that car make a right turn or a left turn? Well, your answer is the car made a left turn. Now, I know it appears to be going to your right, okay? But it's not your right that matters because you're not in the car. You're just an observer outside the whole scene you're observing from. What matters is, what did the person in the car do? What did the car do? And that's got nothing to do with your perspective. That car made a left. Okay? It made a left turn. It went to its left, which happened to be your right. So please, it's not about your perspective. It's not about the viewer. It's about what the object is doing. Now the object makes a right turn. Now the object makes a left turn. Okay, so please, you have to put yourself in the car in order for you to figure out whether this is making a right turn or a left turn. So now, let's take a look at a couple simple problems at the bottom of our page right here. Okay, so what we have here, I'm just going to make this a little bigger so we can take a closer look at it. What we have down here are 4 arrows that I've made for you. So here is your object. What kind of turn is it making? What kind of turn is it making? Is it making a right turn or is it making a left turn? And your answer should have been, it made a right turn. And if that wind or if that missile or if that ocean current was deflected to the right, then what hemisphere must that be in? The answer is northern hemisphere. Now let's try the next one. Here is our vehicle, our wind, our water, our missile, whatever it may be, and it's making a turn like this. Did it make a right turn or did it make a left turn? It made a left turn. That was turning to its left. So therefore, what hemisphere would that be in? That must be occurring in the southern hemisphere. Okay, let's try the next one in its entirety. Say what type of a turn it's making, and therefore what hemisphere would it be? Arrow number 3. So arrow number 3 is making a left turn, and therefore must be in the southern hemisphere. Let's try arrow number 4. Arrow number 4 is also making a left turn, and therefore must be in the southern hemisphere. Okay, so far so good. Let's try another challenging problem here, okay? So now, what I'd like you to do is, and I'm not going to be able to check this in Edpuzzle, but what I'd like you to do is take a look at these arrows that I've given you, and I want you to change the arrow's direction as if it were the northern hemisphere. Now, in the northern hemisphere, the wind or the current or the missile or whatever it is going to be deflected to the right. So this arrow would actually be deflected to the right, like that. Okay, so let's see you try to do the exact same thing to all these other arrows, and we'll see how you did. Okay, welcome back. So this arrow would have been deflected this way. That's to the right. This arrow would have been deflected that way. That's to the right. That's to the right. Now this might look like it's your left, but it's the arrow's right. That one might give kids trouble. Now, yes, the arrow deflected to its right, but that looks like your left, but it's not your left that matters. It's the arrows that matters. Okay, this one here, deflected to the right. This one here, deflected to the right. And this one here, deflected to the right. All right, I hope you got them all right. Now, let's try this. I've given you 10 arrows, making their deflection, and I'd like you to indicate whether this is taking place in the northern or southern hemisphere. This first one, it's making what appears to be a right turn. So therefore, what hemisphere would that be? The answer is northern hemisphere. Okay? So I would like you to put an N or an S with each of these arrows, and we'll see how you did. Okay, welcome back. So This arrow is also making a right. That's northern hemisphere. Left turn is southern hemisphere. Left turn is southern hemisphere. Right turn is northern hemisphere. Bottom row, that's making a left turn, so that would be the southern hemisphere. This one's making a right turn, that's the northern hemisphere. Northern hemisphere, right turn. Southern hemisphere, left turn. And northern hemisphere, that's a right turn. All right, looking good, people. So far, we're making some progress. Now let's try one final problem, or two final problems. Here is a diagram from an old Earth science regions, an excellent one, by the way. The dotted line, the dashed line, shows the original wind direction. The original wind direction. So this is kind of like what you did up on top of the page. The deflected wind result of the Coriolis is shown with a solid line. So this wind originally was going this way, and it was deflected this way. Okay, so very simple. I want you to look at this diagram. Remember your compass directions: north, south, east, west, northwest, southwest, and so on. Please answer 1 and 2 based on this diagram. Pause the video. Let's see what you do. Okay, so a projectile launched toward the north. So let's find that projectile. There's one launched toward the north. So that one in the northern hemisphere is deflected to the, what compass direction is this? The answer is, that's the northeast. Let's try another one. A projectile launched due south in the southern hemisphere. So where's due south in the southern hemisphere? That would be not this one, be this one. It's launched due south. What direction was the deflection? Remember your compass directions. So that one was deflected toward the southeast. Okay, I hope everyone thinks making sense. I hope you understand the two terrestrial evidences of Earth's rotation. Neither the Coriolis effect nor the Foucault pendulum would happen if the Earth were not rotating. They only happen because the Earth is rotating, okay? So, leave any questions at the end. Thanks for paying really close attention, and nice job.